Hello, good afternoon, everyone. Can you hear me?
Good afternoon, sir.
Okay, hi. So I think we can start our lecture now. Wait, where we stop? Okay, I think we are in this part PV system design. Okay, and then I have explained to you step one and step two. Now we should be in the step three. Okay, let's continue on step three. Okay, let's go back to have a refreshment a bit. Okay, so step one is the understanding of the design requirement. Step two is to select the proper or appropriate PV module and also the inverter. And the step three is the determine of the PV system capacity. Now we are in step three. Okay, so let's go ahead. Okay, to determine the PV capacity, normally we refer to the requirement of maybe space, maybe power output requirement. Okay, but most of the case, we will fully utilize the space that we have. For example, this one, based on the available space. So you look on this is the, I think, rooftop. Okay, so based on this rooftop, you have to check how many solar panel you can put in. Okay, so for this case, we don't care about direction yet, because the direction will affect the amount of solar energy hit on the panel. Okay, that one you can calculate using the software. Okay, but the best direction in Malaysia is to face a little bit to south. Okay, so let's say the module dimension is 982 mm times 1954 mm, which is about 1 meter times 2 meter. Okay, so based on this area, how many panel you can put in? Okay, so you can arrange properly lah, and we do not actually need the spacing in between that. Okay, so even we need also varies minimum spacing. Calculate how many you can put. But remember that don't overuse the space. What I mean is some of the space do not have the support at the bottom. For example, some of the rooftop at the side, they do not have the support. Just cover. You can see it, but actually the support is until maybe certain part only. So make sure your panel is fully supported. Okay. So you can see from here, we can put 28 module in the front part of the roof and 21 module at the back part of the module. Sorry, at the back part of the roof. Okay, so total I can have 49 pieces of solar module. This area can fit in 49 pieces of solar module. And let's say one pieces of solar module can supply 320 watt peak. Okay, so the total system capacity is 49 times 320. This is the rated power. This is 15680 watt peak. P equal to peak power, PEAK. Okay, I think no issue. Just number of module multiplied by the power output, rated power output of one module. Okay, so just try to fully utilize the space that you have. Okay, but avoid any space that is a possibility to expose to any shadow. Of course, the shadow aeroplane, no need to take care of it lah. But I mean the shadow of the nearby building or maybe tree. Okay, then definitely we have to avoid that. Okay, let's say front part I can put 28 pieces, and actually there's a one pieces. Let's say this one. If you have 1 hour covered by a tree, okay, so in that case you need to make a necessary adjustment. You can remove this to make it only 27 module, or you need to have a bypass system. So when there is a shadow fall on this panel, then you should have a bypass system to bypass this panel, or else it will become a resistant to the system. Something like accident happen in the highway. Okay, so remember, shadow is very important. Try to avoid it. If you know that this is something that you cannot avoid, the shadow must be there, and you need more power so that you want to fully utilize the space. then you can consider to use the bypass system. Okay, bypass can be an automated bypass or maybe by time calculation. Okay, as long as the resistance is too high, then you just bypass. Of course, you don't need to put the bypass for all the pieces because some of the pieces definitely will not have any schedule for it. So don't waste your money to do the bypass for every pieces. Just do on the specific pieces. Okay. So after we calculate the PV array capacity, which is 15,680 watt, then we need to calculate for the inverter capacity. Okay. So first, this is the power input, which is 100% come from the panel. And then we need to consider the system losses. There are 7 types of losses here, and it will contribute to around 20% to 25% of the power losses. 20 to 25. This standard, you can just multiply by 0.8 to calculate for the inverter power. Okay, so you can see the first one is the irradiant incident refraction loss. Although we can see that the panel definitely will reflect some of the irradiant. If something that cannot reflect any sunlight, it means that you cannot see the thing. It fully absorbs the light, but that's totally possible. Maybe black hole. Okay, but this is not a black hole, so it will still reflect some of the sunlight. Okay. Secondly is the irradiant spectrum loss. Irradiant spectrum loss means that you can see that for the sunlight spectrum, they start from X-ray until the radio wave. This is the entire spectrum. But the problem is not the entire spectrum able to generate current for this photovoltaic module. Remember that you need a wavelength of 1.12 micrometer and below, which only able to knock out the electron to generate the current. Okay, so the rest is actually wasted. So this one we calculate it as a irradiant spectrum loss. There are spectrum, yes, you still have the energy, but not enough to release the electron from the semiconductor. Okay, so partly under the irradiant spectrum loss. Maybe in terms of 1,000 watt per square meter, maybe there is some portion, maybe 50 watt per square meter is actually higher spectrum or higher wavelength, which is not able to use. Okay. The third one is the dirt loss. Dirt loss is mean that the dirt cover on the solar module. Okay. And then the fourth one, the module temperature loss. As we know that when the temperature increase, the power output will decrease, will drop. Okay. And then remember that the solar panel is tested at 25 degrees Celsius, so that you have to consider the module temperature drop. Okay. It means that even at 1,000 watt per square meter and no other losses, you also will never get 320 watt from the panel because the temperature is not at 25 degrees Celsius, which is much higher for loss. This is more referred to the shading effect. Okay. And then number 6, DC cable loss. DC cable loss is where you transfer the energy or the power from the solar module to the inverter. The current is still, the flow of power, current, voltage still in DC, direct current. Okay, so it's partially, we call it as a DC cable loss. Of course, they will always loss. Okay, I think there's an equation to calculate the DC cable loss. Depends on diameter, material of the cable. Okay, and then you can see that we do not consider the AC cable loss over here because AC cable loss is after the inverter. But now we are actually calculate the losses between the input until the inverter. Okay, so AC cable loss not calculate here, but you should calculate after the inverter. When you connect the inverter to the grid, that is another part for cable loss, which is AC cable loss. Okay, and then the last one is the inverter loss. Inverter loss is mean that when you convert from DC to AC, okay, they have the efficiency of 98%. Remember that the spec of the inverter, and that 2% is counted as the inverter loss. So if we sum up all the losses here, it should be contribute to 20 to 25% of the power input. Okay, so the leftover will left only 75 to 80%. So that we do not need to design or select an inverter which have the 100% of power input. Just 75 to 80% we put enough. Okay. The concept here is just to utilize the inverter, not need to over design. Okay, and maybe our practice in Malaysia, we can just multiply with 0.8. Okay, the power capacity for PV multiply with 0.8, you should get the inverter capacity. Okay, but in other country, which is maybe cooler climate, then you have to reconsider the value. Maybe they have a different problem over here. For example, module temperature loss may be much lower. Okay. And after that, now I know that I need, okay, let's say total system capacity is 15,680 and I multiply with 0.8. I don't know how much I get. After 80%, yeah, I get 13,000. Okay, you multiply and see. 15680 multiply 0.8. Okay, so around 12,500. Okay, so I should pick an inverter with the output of 12,500. Okay, so go and check which one is a useful one. Let's say for here, which one is useful? You need 12,500 input. Okay, so you have 9,001, 11,004, 13,007, and 17,010, something like this. So I think it's based on this only. Of course, you have a very wide range of inverter available in the market, not only one. But now let's say we only compare these 6 different models. So of course, I have to choose the Sun 2012 KTL, which the maximum DC input is 13,700 watt, which is the closest to 12,500. Okay, you cannot use 11,400 because too low already. If you want to use that, also can, because you will not fully utilize the power output. Okay, we have to take a balance between the module utilization and the inverter utilization. Okay, so in that case, let's say we pick this one, but that's not yet the end of story. We still have to check the power ratio. Okay, you can see that after you minus 20%, then we have to check the power ratio. Power ratio is the PV capacity divided by the inverter capacity. Okay, and this inverter capacity is actually power output from the inverter, not the power input. So I get PV capacity is 15,680. I divide by the inverter capacity output. Okay, so I divide by 13,200. Okay, so I divide by 13,200. I should get 1.19. Okay, power ratio of 1.19. So what power ratio is considered as acceptable range? You can see if what we apply here. If we are using crystalline module, which is the polycrystalline or monocrystalline, the power ratio should be bigger than 1, smaller than or equal to 1.2. So it's between 1 to 1.2. Okay. But if you are using thin film, the power ratio should be in between 1 to 1.1. You can see that if we use thin film, our power ratio, the tolerance for power ratio is slightly tight. Just because of the thin film will have the more consistent power output. The reason is they do not have high temperature effect and also shading effect. Okay, so for crystalline module, we expect it have the lower tolerance. Sorry, we give better tolerance to it because the power output will have the better difference due to the temperature effect and the shading effect. Okay, and this is what apply in Malaysia industry. Crystalline module, power ratio must be between 1 to 1.2. If you are using thin film module, then power ratio should be between 1 to 1.5. Okay. Any question until here? Okay, maybe something like this. What do you think if I have 2 inverters? One gives you the power ratio of 1, one gives you a power ratio of 1.2. Which one should be better? Okay, this is, we cannot say which one is better. Okay, but if the power ratio is close to 1, what happens? EV capacity, if you're very close to inverter capacity. So in other words, you will not fully utilize your inverter. Okay, because we expect the loss already, but now you still adjust it very close to 1. Okay, but if you make it close to 1.2, yes, you will always fully utilize your inverter. But what happens if the loss is less than 20%? Okay, your calculation, everything is this assumption, but now your assumption is slightly too high. You assume that too much losses already. Then you will waste some of the energy come from the solar module. Okay, so we cannot say which one is better. Just depends on what you want. Okay, so if you want the better power output, your concern is better power output, then you should choose is close to 1. Okay, make sure that all the power from the solar photovoltaic system or solar module can be converted to AC. Then you choose as close to 1 as possible. Okay, but if you just want to have the smaller inverter, want to make the system more effective and cost effective in general, then maybe you can choose closer to 1.2. Okay, but let's say there is a 2 inverter, same price, same spec, not same spec, same price, and the quality also the same. And one gives you the value close to 1, one gives you a value close to 1.2, then I think you should choose which one close to the 1. Okay, which you will not lose any energy from the solar photovoltaic. Okay, but I won't ask until that detail. This is just for your understanding. So as long as your power ratio is between this value, then we should consider it as correct. Okay. So after I check the power ratio, I pick this inverter. I check the power ratio is below 1.2, then fine, I can use this inverter. Okay. So just repeat again. Just repeat. Okay. So I based on the PV array capacity, I estimate the inverter output. Okay, and then based on the inverter output, I select the suitable inverter. After I select, I check the power ratio. If the power ratio fall within the acceptable range, then you can proceed. Okay. Okay, after the perform system sizing, then we need to calculate the PV module performance worst case estimation. Worst case is mean that when the temperature is too high, what is the voltage will be? If the temperature is too low, what's the voltage will be? Why we need to calculate this? Because you can see that the inverter have the maximum power point voltage range. Okay, let's say for the one we select, the maximum power voltage range is 380 volt. So how many panels you want to connect in series so that the voltage will not drop below 380? Okay, in that case, you have to consider the maximum temperature because maximum temperature will give you the minimum voltage. Okay, same thing for 800 volt. You don't want it exceed 800 volt. So in that case, you will consider as minimum temperature. Okay, so you can see that we actually have 3 equations over here. First one is the maximum voltage at open circuit. Okay. Second one, maximum voltage at maximum power. And third one is the minimum voltage at maximum power. Okay, the first one is for safety. Open circuit voltage, normally you won't apply this, just for safety. You don't exceed this value. Okay, and then of course, when you have the maximum voltage, when you have the minimum temperature. Okay, so you can see that when start in the temperature here, 25. The minimum cell temperature. You can see that the value we use, maximum cell temperature is 60 degrees, minimum cell temperature is 25 degrees Celsius. Okay, this is applicable in Malaysia. If you want to build a solar panel in other countries, then you have to reconsider the maximum value and minimum value of the cell temperature. Okay, this is very important. You cannot always consider it 60 and 25. But of course, let's say you want to develop a solar system in desert. Maximum temperature may be higher than 60. Okay, so in that case, how you know the value? Then I think definitely come from experience or maybe any reference from journal or what. Okay, but this is in Malaysia. This is the industry standard. They use 60 and 25. Okay, so you can see that we calculate the maximum voltage by considering how much the voltage drop according to the temperature. But this one, because of the minimum temperature 25, so we can say that it will be exactly the same as stated in the specification. Okay, and then you look on the second one, same thing, because the minimum temperature is 25, so we can get exact VMP STC from the specification. And the last one, Vmin MP. We want to calculate the minimum temperature. Okay, maybe I give you, I'll show you again. Okay, let's say now I want to calculate the voltage. Okay, at 60 degrees Celsius. Okay, so maybe you can calculate from here. You can see that the power will drop negative 0.41% when the temperature increased by 1 degree Celsius. Okay, so you can take this 0.41. Okay, 1 degree Celsius increased by, it will drop by 0.41%. So what if the temperature increased to 60 degrees Celsius? 60 degrees Celsius and that's condition at 25 degrees Celsius means that the temperature increased by 35 degrees Celsius. So you take 35 degrees Celsius, multiply with negative 0.41%. So it means that the temperature will drop 14.35%. Then you multiply with the voltage, maximum power point. We use 36.8. So it should drop 5.28 volt. Okay, so 36.8 minus 5.28, then you will get the minimum voltage. Okay, no need to remember the equation as I said that sometimes it give you a value in terms of percentage, sometimes it give you in terms of value. Maybe the voltage drop by 0.05 volt per degree Celsius. Okay, so no need to remember the equation, but you have to understand the concept behind how actually it is calculated. Okay, so according to this specification of the photovoltaic module, Vmax OC is 45.3, Vmax MP 36.8, and Vmin MP is 31.5. So you can see that we need to use the minimum voltage from one module to calculate the minimum voltage needed connect to this inverter. Okay, remember that inverter, they need a minimum voltage of 380. Okay, so from here we can know what is the minimum number of panels I need to connect in series so that the voltage will never drop below 380 volt. Okay, so you can see after we get the temperature, then we substitute the temperature to get the number of pieces. Okay, so you can see for maximum VOC, we use 1000. Maximum voltage during the open circuit, okay, is 45.3. And then the maximum allowable voltage to the inverter is 1000. If we refer to the spec of the inverter. Okay, you can see maximum input voltage is 1000. Okay, so we take 1000 divide by 45.3, we get 22.07. Okay, it means that I can connect 22.07 pieces of module in series for safety maximum. But of course, we cannot have a decimal point here. Okay, how can you get 22.07 pieces? So we have to round down to 22. Okay, so a maximum allowable solar module can be connected in series if you use this inverter is 22. Don't use 23, yeah? Don't round up to 23. Yeah? If you use 23, it means that when you connect 23 pieces, then your voltage will be more than 1000 volt already. Okay, so you have to round down to 22. And then secondly, Nmax VMP, maximum power point. So the maximum power point range for this inverter is 380 to 800 watt. Okay, So we take 800 divided by 36.8, we get 21.74. Okay, there's no word, we can cancel the word over here. Okay, 21.74. So it means that I need to round down also. So become 21. So this is the maximum number of pieces I can connect in series during the maximum power point. Okay, then you are asked, you can see 22 also maximum number, 21 also maximum number. Which one should I use? You should use 21 for the optimum condition. Okay, in case of you cannot avoid to use, you can use up to 22 pieces. Of course, if you use 22 pieces, it already fall outside the optimum condition, but it's still okay. It's still safe to use. Okay, so 21 is the best. Not 21 is the best. Not more than 21 is the best. Okay, and then you see on the minimum number. Minimum number, same thing. We use the lower range of the voltage, 380, divided by the minimum voltage for each panel, which is 31.52. So we know that I need to connect at least 12.06 pieces, then I round up to 13. Okay, the first two is round down, and the last one is round up. So they fall within the range. Okay, so I get minimum 13. So the best is this, between 13 to 21. I can connect 13 pieces or 14, 15 until 21 pieces in series so that the inverter can operate at the optimum condition. Okay, is that clear? Based on this, we can measure how many I can connect in series. Okay, so for this case, should be in 13 to 21. And how many pieces we have? Remember the previous slide? We have 49 modules. So how I want to arrange? Can I just divide by 2? Seems like cannot. If just divide by 2 more than that, divide by 3. Okay, so you have to arrange these 49 pieces. So maybe you go back to here. Back side is 21 module. Front side is 28 module. Can I say that back side 21, I use 1 input? Or maybe they call it as string. Okay, I connect these 21 pieces in series. Okay, so definitely my voltage will not be more than that. My voltage is just near to 800. Okay, and this one, 28, too much already. I cannot directly connect all in series. But how about if I divide into 2? Okay, so I have the 2 string and then 14 module in series. Is 14 module okay? You can see that minimum is 13. So now I use 14. Okay, so that total I have 3 strings. Okay, 2 strings with 14 module and 1 string with 21 module. So total I have 49 module. Okay, and then you can see that these 2 strings both have the 14 module. I just need 1 maximum power point tracker. Okay, because both of them will give you the same output voltage. Okay, but this one, it will give you a different output voltage. So it cannot be the same. So it means that I need 3 input. Okay, 1 string equivalent to 1 input, and I need 2 MPPT based on this arrangement. So you have to check on the inverter. Can it support 3 input and 2 maximum power point tracker? Okay, I check here. Okay, you can see maximum number of input for this inverter is 4. I need only 3. Okay, fine. Number of MPP tracker is have 2, and I have only 2. So it means that this inverter actually fit my usage, and I can use this for the future development. Okay. Is that okay until this point? How many you can connect in series? How many you can connect in parallel? Okay, no problem. Then we move to the last part. Last part is to estimate the energy yield. This is normally is referred to the commissioning one. So whenever you complete your project, you have to come up to send a report to your customer. Yeah, what is the estimated power output? What is the estimated annual yield? Okay, so based on this, based on this PV system photovoltaic software. Okay, this is the energy modeling tools used by the solar industry to simulate the energy harvest of a potential project site. Okay, you can use this to measure. This include the history data of the solar irradiance at a particular location. Okay, but I'm not sure how accurate is the system. Of course, yeah, yes, need to pay. You need to subscribe for the license. So that's why I didn't show you here because we do not have the license. But if you are in that industry, you should buy this license. Okay. Okay, then let's look on this solar panel. Which direction should the solar panel face? And what is the optimum tilt angle? You can see that some of the system, all the panel face to the same direction. And some of the system, they put it alternate. Some face to the one direction and the other to the opposite direction. So which one is the best? Okay, so which direction should we face? So as we look on the graph, let's say this is the north, south, east, west. And we know that the sun will pass through the north to the east or from the south to the east. Okay, but at solar noon, the sun is exactly on this line, north-south axis. Okay, so in other words, we will always point our panel to the solar node if our panel is the stationary panel. So that we don't need to consider face to east or west, but we face to the north or south only. This is the only choice, north or south. Okay, so north or south depends on your location. If the sun passes through the south, then you have to face to the south. If the sun passes through the north, then you have to face to the north. If the sun passes through the north and south, then you have to choose which side you will pass through in most of the day. Like in Malaysia, Kuala Lumpur, 3 degrees, we face to the south. Maybe I give you one guideline. If the country, the location is located at the south hemisphere, then your panel should face to the north. If the country or location is located at the north hemisphere, then you have to face to the south. Okay, and then of course the angle. In Malaysia, we will use 5 to 10 degrees. But if you use, there is a calculation here. If you are in the other country, let's say, okay, so you can use this system. If your latitude is below 25, use the latitude times 0.87. If your latitude is between 25 to 50, then use the latitude times 0.676 plus 3.1. Okay, so in that case, you will get your angle. Okay, and then this will give you how optimum is the system. So if you follow this equation, you will get the optimal angle of 72. Of course, you will not get 100%. 100% means that you always face to the sun. Okay, so we get 72%. Okay, so let's say we take Kuala Lumpur as a reference. Kuala Lumpur is 3 degrees to the north. So which is below 25 latitude. So 3 times 0.87. So the optimum angle is 2.6 degree for Kuala Lumpur. Okay, but why they use 5 to 10? Okay, this because they want to allow for the self-cleaning. If the 2.6 degree, maybe the dust will easily stick on the panel. Okay, so you need to make a little bit angle so that when the rain comes, it will bring away the dust. So you don't need to clean the panel from time to time. Okay, so in Malaysia, but different company will use the different approach. But 5 to 10% is quite reasonable, but don't be too high. Okay, or else you will not longer face to the sun anymore. Okay, and then another thing, you look on these two figures, you notice that they arrange in different way. One is all the panel face to one direction, one is a left and right. Which one should good? Okay, I can say like this, the figure in the left hand side, all face to the same direction, will have the higher overall efficiency. Okay, but the arrangement in the right hand side will optimize the area. The efficiency was not so high, but you will fully utilize the area. Okay, the reason is you look on the right hand side figure, you need to have a space between line by line, because the shadow of the panel will be at the back of the panel. So you cannot arrange too close, because you want to avoid the shadow to fall on the next line. Okay, so this area is actually wasted. You don't want shadow fall on it, so you wasted a area over here. Okay, why don't you just fully utilize the area by placing another panel which face to the other direction? Because of that shape here, sorry, the angle here, the shadow will definitely won't cover on the panel. You will just get the lower output, but it won't have the shadow. Okay, so that the second system is better in total power output and also in the space utilization. And then the first arrangement is better in terms of the efficiency, because all panels face to the sun. But second system, not all panels face to the sun, but you fully utilize the space. Okay, this is both also okay lah. It's up to you what you want and what your customer want. If your customer say, I want to fully utilize my space, then you use the second one. If the customer say, I want high efficiency, then you use the first one. But I would think that in Malaysia, second one will be more cost effective. Okay, even that is not facing to the south. You see, the optimum one will face to the south, but at the back, it still face to the north. Okay, so you still get a lot of sunlight. But if your location, let's say your location is located maybe 45 degrees to the north. Okay, the latitude is 45 degrees. So whichever panel you face to the south, almost get zero energy. So it will become waste of money. But in Malaysia, this waveform arrangement is very good, because I think 55% of the sun, sorry, 55% of the day, the sun will pass through the south, and maybe 45 of the day, the sun will pass through the north. Okay, so it's actually very close. So this will definitely give you better investment return of investment. Okay, so not every country you can use this waveform. In Malaysia, yes, but some of the countries at very north from hemisphere, sorry, very north from the equator or very south from the equator, normally it's not so suitable, because the other side get very less energy input. Okay. Okay, then I think that's all for the calculation and design of the solar system. Then we go through a little bit before we complete this chapter. The next one is about the concentrating photovoltaics. This is a way to increase the effectiveness of photovoltaics, is to concentrate sunlight on the small, highly efficient photovoltaic cell, okay, which we have it in the East Campus, using inexpensive refractive material, lens, or mirror. These are known as concentrating photovoltaics, CPV. Today, the technology takes up a very small portion because it's still very expensive and it's not cost effective. Although the efficiency is high, but the cost is definitely too high. Okay, so how we make the photovoltaics very high efficiency? Then we have to do it. Okay, we have to do it in this way. Okay, we have 3 layers, and 3 layers made from different material. Each layer will have a different band gap. Okay, so it means that each layer will target on different wavelength. Okay, so the solar spectrum have the photon range for up to 4 eV. You can see some of them 1.88 eV, some 1.4, 0.67. Okay, and then do you notice on the arrangement? On the top, you need the more energy. Okay, 1.88 eV is the band gap. So you need to have at least 1.88 eV to release the electron on this material. And on second layer, you need a minimum of 1.4 eV to release the electron. And last one, you need only 0.67 EV. But how if I reverse this? I put the 0.7 EV material on the top. Okay, remember that 0.67 EV is the minimum energy required to release the electron. If you supply more than that, it's also release the electron. And then the extra energy will become heat. Okay, so if you put the first layer, which is the lowest requirement, then the second and third layer, mostly you won't use it anymore because it will be fully used by this first layer. Okay, so remember to use 3 layers, and the top one should need more energy, so that whichever this first layer cannot be used, it will transfer to the second layer. Okay, remember the arrangement, huh? And this system we call it as a multi-junction photovoltaic, and the efficiency can go up to 46%. As our normal, I think 15, 17, 18 is really good enough, but this one can up to 46% because each layer will give you 15%. So 3 layers will give you around 45, 46%. Okay, this is the highest efficiency photovoltaic that we have right now. But same thing, the cost is also highest. Okay, and this is the entire system for this concentrating photovoltaic. So we call it CPV. Okay, I think you're aware of it, which we have it in the East Campus. Okay, we have the mirror reflect the sunlight into the middle. Okay, and remember that because you focus all the sunlight into the same point, the receiver, I mean the photovoltaic panel, will be actually very, very hot. So in this case, you need to do the cooling. Okay, you see for this case, this arrangement normally we do not supply the active cooling. We just give a space at the bottom. You can see that even I can attach it to the rooftop, but I also will put a little bit space at the bottom between the panel and the rooftop so that the heat can be dissipated. Okay, there can be heat loss by the conduction. Okay, but we do not have an active cooling system which may supply the water or cooling. Okay, because it won't be too hot. But for this concentration photovoltaics, normally it will be very hot because you focus all the sunlight into one point. If without cooling, the temperature can easily reach 100 degrees Celsius. So that we need a proper cooling on this fan. It can be air cooling lah, or maybe water cooling or whatever else, but must be cool. Okay, or else the temperature, the efficiency will drop dramatically. Okay, and this will have the 2 axis tracking, and it will always face to the sun. Okay. Okay, advantage of CPV. They replace expensive PV material with lower cost mirror or reflective material. Solar cells are more efficient at high irradiance level. Due to tracking, production of energy starts early in the morning and extend later in the day because we have tracking system. Okay, high efficiency. And then disadvantage of CPV at high concentration, some heat up and loss efficiency. So they must be cool. Concentrating system use only direct solar radiation because you try to look for the location of the sun, it's tracking. So you are not able to track the sun during the cloudy day. Okay, the system must track the sun. Higher concentration require more accurate tracking. Concentrating systems are more complex than flat plate one and less reliable because you have the moving part. Okay, so until now it's still not widely used lah. Okay, any question before we start to answer this example? Okay, good. Then I think you can try to do this. Wait a minute. But we don't use the solar panel that given in the lecture note. We try to choose others. Maybe. Okay, let's say we use this panel. Okay, Cubic Dual G5, and then you can download. I will send you the link. Okay, you download the specification from the panel from this system. Okay, you go and download and datasheet. Okay, and then use the data from this datasheet. I won't give you the answer first, but you try to get the information that you need from this datasheet. Okay, and then we discuss later. I give you 5 minutes. Okay, and then we start the discussion. You try first. Okay, so let's continue on this. The first thing we need to know is the size. Okay, so if you can calculate until the string configuration, how many you can connect in series and how many you can connect in parallel. But I don't know how far you calculate that. Okay, but first you need to check how many you can fit into the rooftop of the block N by UC. Okay. Okay, inverter model, you can use back the inverter in the lecture note. Okay. Tiong Wei, are you sure? Just divide 1.685. I just spread some of the space at the side cannot be used. Yeah, if one inverter not enough, then you can use more than one. Okay, so let's check the size of the panel. I think you can see my screen now. Okay, so the size is 1685 times 1000. The thickness we don't care, huh? So 1.685 times 1. Okay, so the rooftop is 40 meter times 10 meter and 40 meter times 10 meter. So maybe we check the front part will do lah, and then the back part will be exactly the same. Okay. Diameter and 40 meter. Okay, so can I say I put it in this way? Horizontally. Okay, so this part I can put 10 pieces. How about this part? 1.685. I can put 23.7 pieces. So 23 pieces. So it means that I can put 230 pieces. And both sides 460. Okay. But of course, if you don't want to put like this, you can put the other way around. You can put vertically. Okay, if I want to put vertically, horizontally, I can have the 40 pieces, and vertically, diameter divided by 1.685. 5.9. So I can put 5 pieces on it. Okay, 4 times 20. Sorry, 40 times 5. So I can get 200 at one side. And 2, I can get 400 pieces. Okay, so I think I should put it horizontally. So I can fit in 460 pieces of panel, not 474. Because some of the space definitely we cannot cut the panel into half. But of course, you want to put the combination of the vertical and horizontal also can. But will be a bit difficult. Normally won't do that. Yes, cannot direct divide. Yes, correct. Because unless you can cut the panel into smaller pieces, then you can directly divide. Or else you have to check vertically and horizontally how much you can put, how many pieces you can put. Okay, so in my calculation, maximum I can put is 460 modules. And from here, you can calculate the PV capacity. Okay, Tianlong, yes, good question. Maybe it's not square or rectangular, then you have to check how many you can put in. Let's say your location is like this. It's a round rooftop. So how many you can put it in series? How many you can arrange? Okay, so totally you have to use your mathematics lah. We do not have a fixed idea how to do it, but you can fully utilize the space. But remember, don't use the total area divided by the area of one panel, then you do. As long as you can fit in, then it's correct. Of course, just now I calculate 460 module. If you want to use a combination of the vertical and horizontal panel, then actually you can get more than 460 pieces. Nothing wrong. Okay, you just try to fully utilize the space, but we cannot able to use the total area divided by the area of one panel. Okay, so let's assume that we have 460 pieces. So first, we need to calculate the total system capacity. And 151, let me check. I have to check back the rated power for this panel. Okay, which one you choose? 315 or 335? Or any of them? Okay, you have to choose 335. Okay, fine. There's nothing wrong. This depends on which type of panel you want to buy. So you buy 335, then you use 335. So this one, if we fully utilize the area in block N, we should have the total system capacity of 154.1 kilowatt peak. So after this, you have to calculate the system loss. Okay, we just multiply 20%, so we have the inverter capacity. I just multiply with 0.8 because I consider the loss is 20%. So I get 123.28 kilowatt peak. Okay, and then now you have to select the proper inverter. Okay, which inverter you want to use? We have 123.28. Can I say I use 6 pieces of the Sun 2020 KTL? Can I use this one? Okay, let's say I choose that one. Then we come back. Okay, wait first. What? We check the info. Okay, so this one maximum DC input is 22,500 times 6. And then the AC output power is actually 22,000 times 6. Okay, we check the power ratio. Okay, 22,000 times 6. So is that fall within the acceptable range? 1.167. Okay, and actually what we look for is between 1 to 1.2 for crystalline silicon, crystalline photovoltaic panel. And then what is actually this one? Is this crystalline? It definitely is a crystalline panel. Okay. If it's a thin film, then you should not see the line. It should be a one black panel. without any line in between. Or you want to check, you can check further, see it's written in any line. Yeah, you can see that the cell monocrystalline. Okay. So this monocrystalline, so we get the power ratio of 1.167 is acceptable. Okay, so now you select the inverter, you select you have the power ratio, then you try to calculate for the worst case estimation. Okay, by calculate the voltage maximum. Okay, so in that case, we have to look for the open circuit voltage and maximum power point voltage. Open circuit voltage, run to this. Open circuit voltage 40.92. Okay, and then maximum power point voltage 34.31. Okay, know how to read, because you pick 335. So this is our answer. From 40.92 to 34.31. And the next information we need is the temperature coefficient. Okay. So where is the temperature coefficient stated here? Yes, temperature coefficient over here. So temperature coefficient for what's the value? Oh, negative 0.36. And then your unit, you have to look carefully on the unit. It's a percent per Kelvin. Okay. And then temperature coefficient for VOC is 0.27. Okay. So you have to set the maximum temperature, Tmax and Tmin for the cell. So assume that we do it in Malaysia. So what is the Vmax OC? So you have to think about at maximum voltage. Supposedly it should be at the minimum temperature. Okay, so I think no need to check out. Normally it will definitely measure at the standard test condition. So maximum OC should be exactly same as a VOC because the temperature is at 25 degrees Celsius. Okay, and then we have Vmax. Yeah. MP. Okay, same thing. Maximum voltage is at the minimum temperature of 25 degrees Celsius. So it actually matched with the standard test condition. So we just use the value here, 34.31 watt. Okay, and then V minimum MP. So as we see from here that when the temperature increased by 1 degree Celsius, the maximum power point power dropped by 0.36. Okay, so I can put the original voltage is 34.31. Okay, and then plus negative 0.36. Okay, and then how to write? Because it will drop 0.36%. Okay, so I multiply with the temperature change, 60 minus 25. And what else? I need to multiply with the 34.31 watt. Okay. So maybe you don't need to care about the equation that I write. Just care about temperature increased by 1 degree Celsius. How much drop? Okay, for this case, it dropped by 0.36% for 1 degree Celsius. So this one is 35 degrees Celsius different. Multiply 35. So it will drop 12.6%. So 34.31 minus 12.6%, you will get what? Okay. Where's your answer? The minimum voltage at maximum power point. Share your answer, you already get the answer. Or you have any problem, also let me know. Oh, sorry, Jun. I didn't see your message. I also don't know why. Okay, so we get 29.98 watt. Okay, so based on this and the information from the inverter, we can decide how many we can connect in series and parallel. So first, Nmax VOC. So we go back to the inverter spec. Maximum input voltage 1000, and then maximum power point voltage range is 480 to 800. Okay. So 1000 divided by 40.92 watt. 800 divided by 34.31 watt. 480 divided by 34.31. Sorry, it's not divided by 34.31, it's divided by 29.98. Hey, Munjin, can you check your answer for the last part? Okay, I think correct. Okay, so the first two we round down, sorry, and the last one we round up. So that we come up with a range of 17 to 23 module. This is what we want to arrange. Okay, make your own arrangement. How many pieces we have? 460. Okay. As long as between 17 to 23, then it's okay. But seems like 460 can be divided by 23. Okay. We'll get a round number. $460 divided by 23. Okay, so can I have the string arrangement? Maybe you propose the string arrangement first. I need only one MPPT times 20 string times 23 module. Okay, so you meet my requirement, 23 pieces maximum. Okay, and then I use 20 string. So it means that I need 20 input. Okay, and I need only one MPP. So we go back to check on the spec for this inverter. This can have the 6 input per inverter. So 6 times 6, we can get 36 input. So we just need 20, more than enough. And each of the inverter has 3 input. But again, we need only one input. Sorry, we only need one MPP per inverter. So definitely it beat our requirement. So I can use this. Okay. So end up with, I have designed a system, a PV system, which will give me the power output of 154 kilowatt. Okay. So maybe I summarize: system capacity 154 kilowatt, and I need to use 460 pieces of the module, which 335 watt per module, and I need to have the 6 inverter. 460 pieces of module, 6 inverter, and then the power output is 154 megawatt. Sorry, kilowatt. Kilowatt. Okay, so based on here, we can estimate the power output from the panel already. So normally, how much you can get in Malaysia, maybe just around 20% of the capacity factor. If you do not have a system to calculate, the software to calculate, you can just roughly estimate. Okay, maybe just around 20%. Okay. So 1 MPPT, 23 module. If you don't like this, you can change the arrangement. Don't worry. Let's say you like to have just 20 modules per string. Fine, you take 460 divided by 20, then you need 23 input. 23 input, but for 6 inverter, we actually have 36 input. So it's still fine. Okay, this is how we do it. Okay, Samuel, how to know the number of inverter we need? So definitely it depends on the system capacity. You can see that based on the total system capacity, which is 154.1 kilowatt, then we know that inverter capacity, total capacity for inverter is 123.28 kilowatt peak. Can you see that? 1283. But the only inverter that we have, let's say in the market is only this. Only on this list. Okay, so we need 123 kilowatt, but this one it can only support up to 22 kilowatt, 22.5 kilowatt. Then we just divide, we can know that we need actually 6 inverter. Of course, after this, you still have to calculate the power ratio. Of course, if you say, I don't want to use this, I want to use others. I want to use Sun 2008 KTL. Okay, fine, but you need more inverter. Okay, normally we try to minimize the number of inverter needed. Okay, because normally the size bigger per unit output, the cost of inverter will be cheaper. When the system becomes larger, the price of the inverter will become cheaper. But of course, some of the case, you say you don't want to rely on one inverter. Okay, because let's say this inverter have any issue or you want to service, then the entire farm will have no energy output. So in that case, you may separate the 2 or 3, depends on your need. But you just want to save money, then try to use one big inverter which can support everything. But of course, maybe your system is too big, which you cannot find the proper inverter. Okay. Samuel, is that okay?
Okay, sir.
Okay. Yes. Okay. No. As long as the number of module in each string is how many? It's between 17 to 23. Then it's okay, acceptable. Okay, but remember, if you do it this way, you have more input. You need 23 input. Okay, so you have to check whether the inverter can support up to 23 input or not. But for our case, as we use 6 inverter, we can support up to 36 input. Okay, normally the input and the maximum power point tracker will not actually limitation. Normally the number of input and the inverter needed will be much lesser than what is available, what is supplied by the inverter. Okay, but you still have to check lah. But I never see the case that number of input and the number of maximum power point tracker make a problem. Normally it's definitely enough. Okay, yeah, Munjun, you say the system will generate 186.86 megawatt hour per year. Okay, then let's recalculate. We have how much? 154. 15. Let's say you want to calculate the total energy yield per year. Okay, so let's say the system we need to make assumption. capacity factor 0.2. Okay, let's say capacity factor is 0.2, and then your system capacity 154. So you can calculate the annual energy U. Annual energy U. Okay, so 154.1 kilowatt. You run for 24 and 365 days. Multiply with 0.2. Okay, we still consider 24. I know that you will say, 12 hours we do not have sunlight, but this already calculated in this capacity factor. Okay. Then we get 269. Okay. Munjun, how you get 189 just now?
I used the last time the formula I showed you last time, where it's the area of the solar panel multiplied by the solar panel efficiency multiplied by the annual solar irradiance, and then multiplied by the system loss. I found that the Malaysia annual solar irradiance is around 1,600.
Okay, that one we consider the we consider the efficiency. Okay, but this case you see our calculation we don't consider efficiency anymore. We just see how fast, how much is different from the standard dash condition. Okay, you can see that 154 is mean that at standard dash condition we can get this. But now we are not at standard dash condition, so we add in the loss factor. I think the approach is different, but you should get a similar answer. But of course 0.2 is just my estimation. I just simply put in 0.2. Maybe you will not get 0.2. Okay?
Okay. So then, sir, if I use the method I found online to calculate the yield, would that be considered okay?
As long as you make sure that there's no error over there, then okay.
Okay.
Because I remember last time you showed me, I said something missing, right? Some information missing.
Yeah, because last time I was missing the information, and now I found the information already. So now it's actually considered accurate lah. 80% of the max. The last time this one 365 multiplied by the 20 this one.
Okay then. I think 189 quite reasonable lah. It based on your result, yeah, 189. You see that the capacity factor is 0.1 something. Quite okay, I guess. Quite reasonable lah. Okay, we won't have the very high capacity factor normally for solar, even in Malaysia. In other countries, even more. Okay. Okay, finally, we have completed the chapter for solar energy. Any other question? Okay, how many number of modules we need actually depends on the area. Okay, so based on this area, we can put in 460 pieces of module. Okay, but remember that you are not allowed to get the total area divided by the area of one panel, because some of the area cannot fit in the one pieces of module. It's not like something waffle or what that you can just fill out the area. Not in that way, because the size of the module is fixed. Okay, and then you cannot cut in. Is that what you mean? How to calculate the number of module?
Yes, sir.
Yeah. Okay, this is based on the amount of the area of space we have. Then we calculate this way. We see how many we can fit in. Let's try to fit in the maximum number of module to the area. Okay, this is widely used lah. Mostly, if you want to build something on your rooftop, you will use this approach. Just fully utilize it lah. Okay, but for some of the case, I just want to put the panel to power up or something to power my air conditioning system. Okay, then you have to base on the energy needed for the air conditioning system, and then calculate how many modules you need. There's other story lah. Okay, so you have to go through. Oh, okay, Lee, the front and back is something like the rooftop is like this, right? Have some angle. I don't know how to draw. So maybe here I put it front, here is back. Okay, the rooftop. But of course, some of the rooftop will face to the same direction. But this one I refer to the rooftop of the block panel. So there is a front part and back part. Any other question? Yeah, just not explain on the Samuel problem. If the space is not the problem, then we may consider on the power. For example, let's say AC load requirement. Okay, so same thing, we can use this AC load requirement, and then we do the reverse engineering. Okay, based on this AC load requirement, you calculate the annual energy use. Okay, and then do the reverse engineering to calculate the capacity of the PV module. Okay, gain long. When doing cost estimate, do we need to convert the inverter and solar module in terms of price per watt? This one I think is up to you. Whether you want to put the price in terms of price per watt, or you want to have the total value for the system, then it's up to you. Okay, not necessarily, but normally when we want to compare this farm and the other farm, we will use a price per watt. How effective is your farm, then you use price per watt. Okay, but just want to show the cost needed for to build out the system, then we do not really need to show the price per watt. Just show, oh, I need 6 inverter, how much for one inverter? And then I need 460 module, how much is one module? And plus the installation cost, labor cost, and then what else you need? Okay, maybe some commissioning. Okay, then that will be the total cost for the system. Okay, I think most of the costs come from the solar panel and also the inverter. So actually from here, just now you already can agak estimate how much we can get, and also can estimate what the price for the electricity if you build, whether worth to build or not. Okay, and then how fast you can get back the return of investment. I think definitely worth to try that. Maybe the return investment can be 10 years or a little bit more than 10 years, but still okay, what? Okay. Mention 27 years ROI for solar actually quite high lah. But for other maybe lah. What is actually the title? Okay. Jingwei. Yes, wait. I'll show you. Can you see that I use a capacity factor? If I use a capacity factor, we don't need to consider efficiency anymore because efficiency already included in the capacity factor. Efficiency lah, how many hours you have solar energy lah, and how much the solar area you have lah, everything in this 0.2 capacity factor. Okay, but let's say we don't have capacity factor, same thing, we do not need to consider the efficiency. We just need to consider how much is different from the standard test condition. Okay, because the total capacity is given 154 already. So this 154 kilowatt is already considered the efficiency of the panel. Okay, so it means that I give 1000 watt of solar irradiance and the temperature of the panel is 25 degrees Celsius. The system will give you 154.1 kilowatt output with the efficiency of 19.9. Don't take 154 and then multiply with the efficiency again, because the spec given in the data sheet is already calculated in terms of efficiency. Wow. Okay, Zhongyi, the size of the solar storage is definitely depends on how much you want to store. Let's say you say your power plant is 10 megawatt, then you want to store the energy for how many days? You can see the meaning. It totally depends on how many days you want to store the energy, how many days you need to store the energy. Or just you want to store for 12 hours. Let's say I want to use it in the daytime, I collect the energy, and at the night time, I use the energy. So your storage is actually just need for 12 hours. Okay, so the duration of the storage is very important. So it depends on what is your requirement, how big is the battery need. Or you want to make it store for 3 days, then your battery might 3 times higher. Yes, correct. You have to consider the consumption as well, because not 100% of energy go into the storage. unless the storage, sorry, unless you only use the energy at the night time. For example, just for the street light, okay, or for something just operate at night. Then okay, you have to store 100% of the energy in the battery and use it at night. Okay, so I cannot tell you how much how big is the battery that you need. Munjun, what is your 27 ROI is for which renewable energy? Is that for solar energy? If for solar energy, definitely too high already, 27 years. Yes, a bit too high, 27 years. If you refer to Google, there's a few company offering help you to develop the solar system. I think their return on investment around 10 years only. But how come yours is 27 years? Are you overestimate something? But if you talk about others, so hydropower, 27 years may be okay. Oh, okay. That case maybe because of the structure, you need more cost maybe. Okay, what I mean is you build on the rooftop lah. Because rooftop, you save the area, you don't need to buy the land. And then secondly, the structure, okay, is very simple. So that the cost is normally very minimum. Okay, but now you want to build on the floating on the reservoir, then maybe, 27 years maybe. Because I don't know how much you spend on the floating part. Okay, and then land size. You say need the land size, land and then price, then possible. Okay, I mean 10 years is mean that you don't need to pay for the land. But panel itself already 3.4 billion. Very, very big power plant, maybe yours. But remember that as long as you have the positive return of investment, then should be okay. Okay, but 27 years is, what I mean is, can your panel last for 27 years? Do you consider the degradation of the panel? Normally, they won't last, they won't use for 27 years. Because land price, the cost to pay for the land is pay for one time only. Then you can maybe use for 99 years for the leasehold, or maybe forever for the freehold. Okay, so in that case, you pay for one time only. As long as you get the positive return on investment, then good enough. Okay, warranty is 25 years. So, but your ROI is 27 years. And the warranty 25 years, as I explained previously, doesn't mean that at year 25 you still get 100% output, but just guarantee that you will get maybe 80% of output at year 25, something like this. Okay. Oh, okay. Munjun, then good. When you factor in the degradation. Okay, fine. Then good enough. So that you can see that what actually I want to see in your project on this assignment, what actually you consider. You consider the degradation, now you consider this, you consider that. Everything is just very subjective. Some of you say, I don't want to consider this, I don't want to consider that. So everything is very open-ended. Okay, is you can make whatever you like as long as everything makes sense and reasonable, then I will accept. Okay. Okay, any other question from other members? Tomorrow and Wednesday we have EAC visit. Then hopefully we can get 6-year accreditation. I think some of you has been selected to be interviewed by the panel, so get prepared. So for the rest, I think should be no problem. Yeah, don't worry, you are one of them. Oh, yeah, I see. For RMH, they pick 10 people, 10 students. But for RME, they just pick 2 students per year. Okay, so only one in here is from RME, I guess. I think Wei Long, Pang Wei Long, prepare for yourself for the interview tomorrow. Yes. Okay, RE seems like quite a number kena also. I remember. Wei Long, Pang Wei Long. I remember from RE. Okay, we have for 20 minutes left. I think okay lah, no need to continue. Initially, I think I can complete this in 1 hour, and then another hour we can do it for wind energy. Okay lah, I think we can complete before the semester end. Don't worry. Okay, so if no more question, then I think we can dismiss early today. Any other question before we dismiss? Okay, no question, huh? Okay, so thank you very much and see you next week. Okay, bye bye.
Thank you, sir.
Okay, thank you, Deng Wei.
Thank you, sir.
Okay, thank you.
Thank you, sir.